Hey everyone, thanks for joining us today on this video about Chebyshev's inequality. My name is Bereket Kinda. In this video, we will talk about Chebyshev's inequality as a continuation of what we started in the last two videos, where we talked about Markov's inequality. Okay, we will explain Chebyshev's inequality and also use Markov's inequality to prove Chebyshev's inequality. Okay, I hope you enjoy this video. And if you like it, go ahead and subscribe to the YouTube channel and feel free to share it with your friends as well. Okay, let's get to it. I will start with a motivating example. In 2019, over 2 million students, high school students in the United States took the SAT exam. Okay, and the average score of the ACT exam for that year was 1,059 with standard deviation of 210. That means the variance is 44,100. Now, I'm going to ask you a question. If X is a random variable that represents the SAT score of a high school student, what is the probability that a student gets a score that is outside of 315 units or points from the average? So the average was 1059. So what is this probability? We can answer that question precisely when we know the distribution this random variable follows, which in this case, we know it's normal distribution. Typically, SAT scores follow a normal distribution. To rephrase what I just said, the probability that the absolute value of X minus mu greater than or equal to 315 means what is the probability that a score is either 1374 or more, or it is less than or equal to 744 outside of 315 points from the mean in either direction. I'm going to use a software to calculate this probability quickly, but you could use normal probability distribution lookup tables as well. I will go ahead and use R. So I've got R Studio open here. If you want to calculate the probability of observing above or below some value of a normal distribution, you use the function p-norm. P-norm. It takes a quantile value, and it takes the average, the standard deviation, and whether you want the probability to be in the lower tail or the upper tail. So for this example, mu, the average, is 1059. And the standard deviation, which I'm going to use SD to represent that, is 210. So we want to calculate, first, we want to calculate the probability on the right-hand side here, the probability of observing a score above 1374. Okay, so that is p-norm, 1374, that's the quantile value, and the mean is given by mu, which I have as 1059, and the standard deviation is 210. And we want the right tail probability. Okay, that's the right tail probability that we want. So for that reason, we will use lower tail equals false, means right tail equals true, kind of. And we get, okay, that probability is 0.06680. Normal distribution is a symmetric distribution. So the shaded area in the left here will also be exactly equal to the shaded area on the right. But for the sake of, showing that it is true, I'm going to go ahead and calculate that as well. So p-norm, 744, less than or equal to 744, 744. Again, the mean is mu, the standard deviation is still 210. Now I want a lower tail. Lower tail equals true. And we get exactly the same value if I run that line, 0.06680. So the probability I'm interested in, a student scoring above 1374 or below 744, that is outside of 315 points from the mean is the sum of these two probabilities. So I'm just going to add them up, and I get 0.13361. Okay. Now, this probability is equal to 0.13361. Now, this is because we knew that this random variable followed a normal distribution. What if we didn't know what the distribution of the random variable is? Oh, by the way, you can go ahead and calculate this on your own. For a normal distribution with the same mean as we did in the previous example and the same variance, what is the probability of observing a value outside of 420 points from the mean? What if we do not know what distribution a random variable follows? Can we make a statement about the probability that random variable x takes values a units away from the average mean? All right. Chebyshev's inequality gives us a way to make a statement about this probability, and that it gives us an upper bound, the maximum value this probability can take. Now, Chebyshev's inequality is stated as follows. For a constant a greater than 0, this is one way you will find Chebyshev's inequality in textbooks and resources. For a constant a greater than 0, which is here, and random variable x, suppose you know the expected value is mu, and the variance is sigma square for that random variable, and the variance should be greater than 0. It should be greater than 0 so that it actually varies. Then Chebyshev's inequality gives us the upper bound to this probability as sigma squared divided by a square. Let's say we have a random variable x. We do not know what distribution this random variable follows. Perhaps it is a normal distribution, or some sort of bimodal distribution, or it could even be a mixture of discrete point mass and some sort of continuous distribution as well, or it could be a discrete distribution. All right, so we don't really know for any sort of distribution, which we have no idea about. We know, though, that the expected value of x is mu. I'm going to use the same numbers, 1059, as I used before. And we know also the standard deviation. So therefore, the variance is the standard deviation squared, and that is 210 squared. What is the probability of observing values 315 units, so 315 points away from the average? Can you make a statement? Now, Chebyshev's inequality lets you do that. This probability has an upper bound of sigma square, which is 210 squared, divided by a square, where a, in our example, is 315 squared. A is 315. So the upper bound is 0.444. Chebyshev's inequality is telling you for any distribution, this probability cannot exceed 0.444. And this value, 0.444, is higher than what we found with exactly same expected value and variance above for the normal distribution. What did we find that to be equal to? We found that to be equal to 0.13361, and that is less than or equal to 0.444. So when we know specifically what distributional random variable follows, we can be precise. So for the reason that Chebyshev's inequality needs to be true for any distribution, as I said, unimodal, continuous, bimodal, trimodal, multimodal, continuous, or a mixture of discrete and continuous, or just discrete, or any sort of distribution. Since it needs to be true for all of these scenarios, the upper bound tends to be conservative. That is, it's higher than what you would find this probability to be if you knew what distribution this random variable follows. There are actually inequalities sharper than Chebyshev's inequality when you actually know it's, well, the distribution is unimodal. That's an information you can go with and then make this inequality more precise. Okay, but since this needs to be true for all sort of distributions, it tends to be conservative. Let's go ahead and prove Chebyshev's inequality using Markov's inequality we have learned in the last two videos. Markov's inequality, let's say we have a random variable y that is non-negative. Non-negative means the probability that y takes values of 0 or more is 1. That is, it only takes values greater than or equal to 0. It cannot be negative. Okay, and it is not degenerate at 0. That means the point that the probability cannot be aggregated just at 0. It needs to vary. And for a constant s greater than 0, Markov's inequality tells us the probability of y greater than or equal to s is less than or equal to the expected value of y divided by s. I'm going to briefly mention this because I've done 2 videos on Markov's inequality, and I will have a link to them in the comments section and the notes section of this video. Okay, now we can use this information to prove Chebyshev's inequality. The left-hand side of Chebyshev's inequality for a random variable x is, as we have just seen before, the probability that the absolute value of x minus mu is greater than or equal to a constant a. That is the left-hand side of the inequality. Let's find the upper bound for this inequality. If I square both sides of the expression inside the probability function, I have x minus mu squared. The probability that x minus mu squared is greater than or equal to a squared. When you square any number, whether it's positive, negative, or 0, you get a value greater than or equal to 0. You get a non-negative value. So since this expression is non-negative, which is one of the conditions of Markov's inequality, let's say y is equal to x minus mu squared. And then the constant s, which is greater than 0. Again, a squared is always greater than 0. If a is greater than 0, let's say that is represented by s. If I just apply Markov's inequality, the upper bound is the expected value of y divided by s. So this expression is less than or equal to the expected value of y, which y is x minus mu squared, divided by s, which in this expression is equal to a squared. If you look at the numerator here, you have squared deviations from the mean. Deviations from the mean squared, and then you take the expected value. And that is precisely the definition of variance. So this is, the numerator is sigma squared. All right. So what I have here is this expression here is equal to sigma squared divided by a squared. And therefore, the probability that the absolute value of x minus mu is greater than or equal to a is less than or equal to sigma squared divided by a squared, which is exactly what we had as Chebyshev's inequality formula. Okay, so we proved Chebyshev's inequality. So we have proved Chebyshev's inequality. Now, the last thing I want to do, maybe one of the last things, I might add something if I have time, if it's not going to make the video very long. There are equivalent ways to write Chebyshev's inequality, and this is one of them. However, in statistics, we typically care about, if you have some sort of quantity that you want to estimate, a random variable quantity that you want to estimate, you want to know how far away from the average this quantity you are estimating is. Okay. In fact, what you typically want to find out is how likely is this random variable to take values outside of k standard deviations from the mean. I'm just going to take an example. Let's say 2 standard deviations away from the mean on either side. Okay, 2 sigma. Okay. So in that case, what you're doing is you're replacing a, this constant a, by k times sigma for k greater than 0. 2 standard deviations away from the mean, or 3 standard deviations away from the mean. If you're interested in that, then you can rewrite this Chebyshev's inequality as the probability that the absolute value of x minus mu is greater than or equal to k times sigma. Okay, so you replaced a by k times sigma. And this is telling you what is the probability that you observe k times sigma k standard deviations away from the mean in either direction. And by Chebyshev's inequality, this is less than or equal to sigma squared divided by a squared, but a squared is what? Sigma squared divided by a is k times sigma squared. So k times k squared, sigma squared. And the sigma squared cancels out, and then you have 1 divided by k squared. It gives you a really nice formula. 1 over k squared is the highest value this probability can take. Simple example, for any distribution, what is the probability of observing values 2 standard deviations away from the mean? That would be equal to 1 over 2 squared, which is 0.25. 0.25 is the maximum probability of observing values 2 standard deviations away from the mean for any distribution. Okay, I wrote that as well, and I'm going to skip that. Okay, here's another one. Okay, so sometimes you will also want to write Chebyshev's inequality in a way that you want to have the probability of observing values within k standard deviations from the mean. So the complement of what you have here, the complement of the blue shaded is this orange color, I think, this orangish color. So that is the complement of this is the absolute value of x minus mu less than k times sigma. What is the probability of observing values within k standard deviations from the average? And that is equal to, well, if this is at most 1 over k squared, then this complement must be at least 1 minus 1 over k squared, okay? And this is yet another equivalent way that you will find Chebyshev's inequality written in other resources. All right, so what we have shown right now is 3 different ways that you might find this inequality written, and they're equivalent. The last thing I want to do, one more thing, I think I've got time. It's sometimes interesting to think about, when is this inequality very tight? I'm going to write down the inequality again. Let me change this color back to black. So the inequality, Chebyshev's inequality, is the probability that the random variable x minus mu, the absolute value of that is greater than or equal to a, is bounded by sigma squared divided by a squared. Now we have less than or equal to here, right? When is that equality portion of this inequality true? When is the left-hand side strictly equal to the right-hand side? And this is one scenario. Suppose you have the average mu right in the middle. For this example, the probability, I'm going to write it out here. X takes a value of mu with probability of, for this example, I think that's 0.8, with probability 0.8, which is 1 minus p. X takes a value of mu. And with probability of 0.1, x takes a value of mu minus a. With probability of 0.1, that happens. The random variable also takes a value of mu plus a units above the average, with probability of 0.1, which is p over 2. So in this case, p is 0.2. Okay, for this example, p is 0.2. Now, for this situation, when you have point mass at a units away from in either direction from the mean, and a point mass at the mean, mu, and the point masses at the tail ends are equal, the probability masses are equal, then the strict equality of Chebyshev's inequality is satisfied. So let's work that out. So the left-hand side is the probability of observing a units from the average. So that would be the sum of these 2 point masses. So the left-hand side, the probability of x, the absolute value of x minus mu greater than or equal to a, is equal to the sum of these two. For this example, 0.1 plus 0.1, which is 0.2, or in general, that is equal to p for this, p plus 2 P over 2 plus P over 2. How about the right-hand side? What is this, the variance of this random variable? What is the variance of this random variable? Okay. Variance is the expected value of x minus mu squared, right? And the probability of x taking a value of x, as x can be mu minus a, or mu plus a, each with probability of, for this specific example, 0.1, 0.8, and 0.1. How about x minus mu squared? So when x takes mu minus a, x minus mu takes a value of mu minus a minus mu, which is minus a squared. And that happens with probability of 0.1 or p over 2, okay? Plus, when x is mu, x minus mu is mu minus mu, well, that's 0. 0 squared is 0. So 0 times whatever probability, which is 1 minus p actually. 1 minus p, which in this example is 0.8. Plus, when x is mu plus a, x minus mu is a. So a squared happens with probability of p over 2. So if you sum these three quantities up, you get the variance, sigma squared, which is equal to p times a squared. Sigma squared divided by a squared is equal to p times a squared divided by a squared, which is equal to p, which is exactly the same as the left-hand side. So this is a situation where the strict equality of Chebyshev's inequality is satisfied. Okay, I think that's all I have for today. So we've looked at several things. One is that we explained Chebyshev's inequality. We proved it using Markov's inequality. And we looked at 3 different ways that we can write Chebyshev's inequality. Also, we looked at situations where the left-hand side and the right-hand side of this inequality are exactly equal. So what are the situations where the inequality is tight? Okay, so I hope you enjoyed this video. Again, go ahead and subscribe. And I hope to see you next time in another lesson.